Okay, in the last class, we started to discuss the quantum mechanical model of the hydrogen atom, and we have derived the Schrödinger equation for the electron in the hydrogen atom, and then we also saw how this Schrödinger equation can get solved. At least we outlined the process, and the result was that there are three-dimensional wave functions that are a function of three quantum numbers: the quantum number n, the quantum number L, and the quantum number m. And the overall wave function that describes the three-dimensional standing waves, or as we call them also, the orbitals, can be separated into a radial wave function and two angular wave functions. Okay, the colatitude wave function and the azimuthal wave function. So now, if we just enter the quantum numbers into the general form of all the orbitals, then you get the specific mathematical descriptions of the individual orbitals. And that's what I want to do today. So let's start with the most simple orbital. That's the 1s orbital. So the 1s orbital is nothing else but the wave function in which the quantum number n is equal to 1, the quantum number L is equal to 0, and the quantum number m is equal to 0. So basically, that 1 here is representing the principal quantum number n, and it's called an s orbital because the quantum number L is equal to 0, so S actually stands for sharp. You probably all know that from previous classes. So if you enter n equal to 1, L is equal to 0, and m is equal to 0 and calculate, then your wave function adopts this form here. And that's essentially the wave function for the 1s orbital. So it's actually shown here as the product of the two angular wave functions and the radial wave function. So when you analyze that wave function, you see that the two angular wave functions, they are simple numbers. Okay. So for the first one, it's that's the azimuthal one. That's the number is 1 over the square root of 2 pi. And for the other angular wave function, the number is 1 over the square root of 2. Okay. So therefore, basically, these are just coefficients in front of that radial part of the wave function. So you see that the radial part of the wave function is an exponential function. Okay, it has the form e, that's the Euler number, to the power of minus r over a0. So r is nothing else but the distance of a point from the origin, which is the center of the atom, and a0 is the so-called Bohr radius. Okay, so that's the first radius of the electron in the hydrogen atom according to the Bohr model. And remember, we had exactly calculated it. It was 5.29 times 10 to the minus 11 meters. Okay. So then we see that we have also here a simple coefficient in front of that exponential term, which is 2 over a0 to the power of 3 hardware, where again a0 is the Bohr radius. Okay, so again, this is just a simple number. So overall, we have a constant times e to the power of minus r over a0. So that means that the wave function will actually exponentially decline as we go from the center of the atom and then further away from the nucleus. And you see here how the shape of the radial function looks like. It's exponentially decaying as we go further and further away from the nucleus. You see here that the radius is listed as in the units of A0. Okay, so whereby A0 is again the Bohr radius. So now that has implications for the probability to find an electron within the hydrogen atom or within the 1s orbital, if we again look at the electron as a particle. Because remember, the square of the wave function always represents the probability to find an electron at a particular point in space. Okay? So now, from this curve, it's apparent that basically the square of this exponential wave function would also be an exponential function that would decline exponentially as we go further away from the nucleus. So that implies that actually the probability to find the electron at a point in space closest to the nucleus is the highest. And then that probability exponentially declines as we go further away from the nucleus. Okay? So that also then influences how we can actually depict an orbital. Okay? So one way to depict an orbital is this. Okay? So each point here represents basically the amplitude of the wave function, which would then also represent the probability to find the electron at a particular point in space. And you see the density of these points is the highest directly at the nucleus, and then the density of points becomes smaller and smaller and smaller, okay, as we go further away from the nucleus. Okay, meaning the amplitude of the wave function becomes smaller and smaller. And also the probability to find the electron at a particular point in space becomes smaller and smaller. So now this exponential function actually just approaches zero as we go infinitely far away from the wave function, but it actually never becomes exactly zero. So that now creates a question, which is, well, how could we define the size of an orbital? Okay? If we wanted to include all probability to find the electron somewhere in space, our orbital would become infinitely large. Okay? And that would make a whole lot of sense to define it that way, because as you would see, also all the other orbitals would become infinitely large, and the hydrogen atom would actually be infinitely large. So therefore, we introduce a specific definition for the size of an orbital, which is that the size of the orbital is basically defined by the radius that would define the volume in which the probability of the electron to be found is at 90%. Okay, so doing that, we can then define the 1s orbital as a sphere, okay, that has specific radius, and that radius is defined by that 90% probability. Okay, so now we need to understand also what is called the radial probability function, okay, which is different from the probability function itself. The probability function is only the square of the wave function, and defines, well, the probability to find the electron at a particular point in space within the atom. But we are also interested, what is actually the probability to find the electron at a particular distance, on a particular radius, okay, around the atom, okay? And that distance actually defines it as a sphere that has a particular radius, okay? And so in order to, well, find out, well, what is the probability to find the electron at a particular distance from the nucleus, we must multiply the square of the wave function with the radius, with the mathematical formula for the surface of a sphere. Okay? And that defines then the radial probability function, which is 4 pi r squared times the probability function. Okay? So now, interestingly, because we have now, well, r squared in front of, well, the radial probability function square, which is, well, an exponential function, and we have multiplied these two functions, the radial probability function now does not just exponentially decline as we go further and further away from the nucleus, okay? Because when you enter r equal to 0 here, you see that the entire function becomes 0. Therefore now, at r equal to 0, the probability is 0, okay? And then the probability increases due to that 4 pi r squared term until the exponential function takes over and we are going to a maximum, and then we are declining again in probability. Okay? So that means when we look at the probability to find the electron at a particular distance from the radius, we will find it, well, not at r equal to 0, but somewhat further away. Now, if we analyze where exactly that maximum is, we find something very interesting. It's actually exactly at the Bohr radius, A0. Okay? So now that makes a nice connection between the quantum mechanical model of the hydrogen atom, okay, the wave mechanical model, and the Bohr atom model. All right? Well, the Bohr atom model said, well, my electron is a classical particle that goes at discrete orbits around the atom. The quantum mechanical model says, well, this is kind of true, but not exactly true because of the wave properties of my electron. Okay? Rather than that, only the probability to find the electron at the Bohr radius is the highest, but because of the wave properties of my electron, there's also certain probability that my electron is being found somewhere else at another distance. Okay? So now, in a way, we can now also explain why the atom is actually not collapsed. Okay? That was a problem that the Rutherford atom model already had, and the Bohr atom model also had that problem. Yeah? And actually, the fact that the probability function, not the radial probability function, has the highest probability at r equal to 0 answers this question. Okay? If you look only at a single point in space, indeed, the probability to find that electron is the highest directly at the nucleus. Okay? So in a way, the atom is actually collapsed, right? But again, due to the wave properties of the electron, well, the electron can also be found somewhere else, or not only closest to the nucleus. Okay, in fact, the highest probability to find the electron at a particular distance from the nucleus is equal to the Bohr radius. Okay, so you see that the wave mechanical, the quantum mechanical model resolves all the problems that the previous atom models had. Okay, so now we have looked at the 1s orbital, and in the ground state, our electron in the hydrogen atom is in the 1s orbital. But of course, that doesn't mean that the hydrogen atom only has a 1s orbital. It of course also has many other orbitals associated with all the other quantum numbers. It's just that these orbitals are usually not occupied unless our hydrogen atom is in an excited state. Okay, therefore let us now look at all the other orbitals as well. So now we can increase, for instance, the quantum number n from 1 to 2, then we go from the 1s orbital to the 2s orbital. Okay, so you see here the wave function for the 2s orbital. So you see again that the angular parts of the wave function are simple coefficients. By the way, this is the reason why s orbitals are spherical orbitals. Yeah. So there are no angular components to that orbital. Thus, all orbitals actually being spherical. Now, the radial part of the wave function has a somewhat more complex form as previously. So you see here again a simple coefficient. Okay, that again is just a number. It's 1 over 2 times the square root of 2 times the Bohr radius to the power of 3.5. And please don't memorize these coefficients. Then we have again here our exponential term. So we have again e to the power of minus r. Now that's all divided by 2a0. But you see, essentially we have the same kind of function, e to the power of minus r. But now we have here another term, which you see here in brackets, which is 2 minus r over a0. So that term now introduces a node into this orbital. And that node is called a spherical or radial node, because unlike the node of one-dimensional waves, the node is not a point, but it actually defines a sphere. That is due to the three-dimensional nature of the orbit. Okay? So we can easily see where actually this node is. And we can determine this by investigating at which radii does this term here become 0, because when this term here becomes 0, the entire wave function becomes 0 and we define a node. Okay, so that would be the case for 2 minus r over 0 is equal to 0. So we could just resolve this term for r, okay, and the result would be that r is equal to 2a0. Okay? So at 2 times the Bohr radius, we would have here a node at which the orbital changed its algebraic sign, or in other words, the wave function associated with the orbital changed its algebraic sign. Okay? So the amplitude would go from positive to negative. Okay, so overall, our wave function would have the following form. We would have here, again, an exponential decline. And then here at 2a0, the amplitude would be 0. And then our amplitude would become negative, go here through a minimum, and then the amplitude would approach 0. Okay, so if we wanted to again depict our orbital, we could do it the following way. Indicating the algebraic signs of the amplitude by different colors. So we could, for instance, define orange to be positive and blue to be negative. Okay? So then the density of orange points would first exponentially decline as we go further away from the nucleus, but then it r is equal to 2a0, the algebraic sign of the wave function would change, okay? And then the amplitude would increase again, okay? Because we have here this minimum, which is just the negative maximum in a sense, yeah? The absolute value of the amplitude would here be maximum, after which the amplitude of the wave function would again decline until it becomes eventually, it's approaching 0. Okay, so you see that the area where the algebraic sign changes its wave function is defined by a spherical surface. Okay, therefore we say this is a spherical node. We can also call it an angular node. Again, we could define the probability. We could define the size of the orbital as the volume in which the probability to find the electron is 90%. Okay, that would depict our orbital then, all like that. All right. Now again, we need to distinguish between the probability function and the radial probability function. Again, when we just look at probability, then we will find again that the probability to find the electron at a specific point in space is the highest directly at the nucleus. Okay, that's just because the amplitude of the wave function is the highest, the closest to the nucleus. But when we again ask, well, what's the probability to find the electron at a particular distance, then this is no longer the case because we must multiply the probability function with the surface of a sphere. We must multiply it with 4 pi r squared. And then our function looks like this. Yeah. So we have actually a function that has now 2 maxima. Here a small maximum first. So here at this point we have the node, and that means that also the radial probability function must be 0 at this point. But then we have here this very big additional maximum, after which the radial probability again declines. So this means that this here is actually the radius on which the electron is most likely to be found. Okay? You see now that this is somewhat further away, actually a lot further away in comparison to the 1s orbital. So in the 1s orbital, that distance was 1r. You can see here from the graph that for the 2s orbital, it's actually about 7 times a0. Yeah. So that means that our 2s orbital is much larger than our 1s orbital. This is a general trend. The higher the quantum number n in an s orbital, the larger the orbital is. Okay. Now we can go from the 2s orbital to the 3s orbital. So now our quantum number n is equal to 3, and our wave function adopts now this form. So you see again, the angular parts of the wave function are just simple coefficients here and here. Yeah. So again, our orbital would be spherical. Now our radial function is now again a step more complicated. We have again this simple coefficient here, which is just a number. We have here this exponential term. It's now e to the power of minus r over 3a0. But again, in the middle here, there's a term in brackets. It's 27 minus 18r over a0 plus 2 times r squared over a0. So you see that this now represents a square function, okay? And you know that a square function has that general form here. F of x is equal to ax squared plus bx plus c, and you know that such a function has 2 solutions, okay, which is given by this formula here. X is equal to minus b plus minus the square root of b squared minus 4ac over 2a. Okay, so that means now that we do not only have one spherical node in our orbital, but we have actually 2, okay? Because there are 2 solutions for which that term here can become 0. Okay? So now, again, we can depict our orbital accordingly. So here again, the density of points representing the amplitude of the orbital. Again, orange stands for positive algebraic sign, blue for negative. So initially, our wave function has a positive algebraic sign. Then we have our first spherical node, where we switch to a negative algebraic sign. And as we go further away from the nucleus, we have again a spherical node, where we have again a positive algebraic sign. Okay, you see here also the amplitude of the radial function, which corresponds to this picture. So again, we have an exponential decline as we go further away from the nucleus, but then we have here our first spherical node at this distance. Then we go through a minimum where the absolute value of our amplitude is maximum. Then we go here to our second spherical node. We have here a second maximum. And then eventually the amplitude of our wave function becomes 0. So again, also in a 3s orbital, the probability to find the electron at a single point in space is the highest, the closest to the nucleus. Yeah? Close to absolute, directly at the nucleus. But again, if you want to ask, well, what's the probability to find the electrons at a particular distance, that's no longer the case, because we multiply the probability function with the formula for the sphere, the formula for the surface of a sphere, okay, here, and then our curve looks like that. So at r equal to 0, well, our amplitude is 0, or our probability is 0. Then we go here to our first maximum. So that represents our first spherical node, where again the probability must be 0. Then we go here to a second maximum. And then again, that point here represents our second spherical node. And then, sorry. I'm confusing myself. So here, here this is our second spherical node, and then we go here again through a minimum, and that's now here our third spherical node, and then we go through a maximum again, and after which we eventually approach 0 probability as we go very far away from the nucleus. Okay, so this this distance here, yeah, you see it's now approximately 12 times the Bohr radius away from the nucleus, is the radius on which the electron is most likely to be found. Okay, that again tells you the 3s orbital is larger than the 2s orbital, which is larger than the 1s orbital. Okay, so now we have discussed s orbitals in sufficient depth. Now let us go from s orbitals to p orbitals. So now, when we have a p orbital, then the quantum number L is no longer 0. So the p orbital with the lowest quantum number n is the 2p orbital. We cannot have a 1p orbital, yeah, just because the requirement, because of the requirement that L can only run from 0 to n-1. Okay, so now for the quantum number L is equal to 1, we can have different quantum numbers m. Okay, so quantum number m can run from -L to +L. So when L is equal to 1, m can adopt the values -1, 0, and +1. And that means that we can have 3 p orbitals. So let us look first at the one with the quantum m is equal to 0. So that refers to what is called 2pz orbital. But we will understand in a moment why it's called the pz orbital. You see here now the explicit form of the wave function. So when you now look at the radial parts of the wave function, you see that now one of the angular parts of the wave function is now not a simple number anymore. It is now a function of an angle, in this case, a function of the angle theta. Okay, so that means now that we would not expect anymore that our orbital is spherical. It should have a non-spherical shape. Okay, so now when you look at the radial part of the wave function, you see again that we have here a simple coefficient. We have here again our exponential term. It's e to the power of minus r over 2a0 in this case. But again, we have a term in the middle here, and that's r over a0. So now because of this term, at r equal to 0, our amplitude is being 0. And that's a big difference to the s orbitals. So in the case of p orbital, the amplitude of the wave function at r equal to 0 is 0. Okay? So we have a linear function multiplied with an exponential function, because of which we have first an increase in amplitude, and then we go through a maximum, okay? And then eventually we get a decline of the amplitude, and the amplitude will eventually again approach 0. Okay? So that's the fundamental difference between s orbital and a p orbital. In the s orbital at r equal to 0, the amplitude is maximum. For p orbital, the amplitude is 0. And that's because p orbital has this term here. Okay. Now, what about the probability function? Now, also for a simple probability function, no longer the point in space at which the probability is the highest to find the electron is at r equal to 0. Okay. Rather than that, the probability is actually 0. Okay. So in this case, the radial probability function also goes to a maximum. The probability function also goes to a maximum, just like the actual wave function does, and then declines. So in this case, the radial probability function multiplied with the formula for the surface of a sphere, has a very similar shape. You see it actually here. Okay. At r equal to 0, the probability is 0, then we go to a maximum, and then as we go very far away from the nucleus, the probability becomes 0 again. So this radius here would be the radius with the highest probability where the electron can be found. Okay. So now to the question, which shape should we actually expect for the 2p orbital? We've already said that, well, it should be non-spherical, but if it's non-spherical, what is the precise space actually? And this question is easier to be answered if we transform the angular part of the wave function back from spherical polar coordinates to Cartesian coordinates. Okay, then this part of the overall wave function adopts this form. Of course, I'm omitting here all the mathematical steps, but just present you the end result of the calculation. So the product of the two angular parts of the wave function is half times the square root of 3z over pi r. Okay. So now we need to think about, well, under which circumstances does this product here become 0? Because that would define again a node that would determine the shape of the orbital. So now this product here will become 0 for z is equal to 0. Okay? So in three-dimensional space, the coordinate z is 0 within the xy plane. Okay, because in the xy plane, x and y can adopt any value, but of course the z value must be 0. And so that means that the wave function, or the amplitude of the wave function, must be 0 within the xy plane. Now that defines the shape of the orbit, because the xy plane must be a node within that orbital. So in this case, it's not a spherical node, but a planar node. A more general term for a planar node is an angular node. Okay? So this is why the PZ orbital has its shape. It has this dumbbell shape, okay, with different amplitudes in the different lobes here, and the XY plane here just separates these two lobes, because it's a node where the algebraic sign of these two lobes must be different. Okay, naturally that means that our 2pz orbit is oriented along the z direction. Okay, so that's why it has the name, or more precisely, it actually has its name because it's a linear function of z, yeah, according to this expression here. This is actually why it's called pz. Oh, it's a linear function of z. Okay, so now we have understood our pz orbital, 2pz orbital. So now what about the other two? The 2px and the 2py. So for the 2px and 2py, m would be plus 1 and minus 1 respectively. So you see here the respective mathematical terms for these two orbitals. So in this case, only the angular part of the wave function changes. The radial part of the wave function is exactly the same as for the 2pz orbital. So you see that for the 2px and 2py, also the azimuthal part of the wave function is now a function of an angle chi. Okay. The colatitude part of the wave function again is a function of an angle theta. Okay. So again, we would expect that this orbital is non-spherical, but what shape would it have? Again, we can answer this question by transforming the angular part of the wave function, which is that product here, from spherical coordinates into Cartesian coordinates. Okay. Then for the px orbital, the product would be a half times the square root of 3x over pi over r, or pi r. And for the py orbital, this product would be a half times the square root of 3y over pi times r. So again, we need to think about, well, under which conditions would that term here become 0? Well, for the px orbital, it becomes 0 when x is equal to 0. So x is equal to 0 in the yz plane. Okay. Therefore, for the px orbital, the yz plane now represents a planar node, which defines the shape of the orbital, which is now oriented in x direction. Okay, because the algebraic sign of the wave function must change at a node, the two lobes must have different algebraic signs. Now for the 2py orbital, which is a linear function of y, the wave function becomes 0 when y is equal to 0, and y is equal to 0 in the xz plane. Therefore, now the xz plane represents a planar node for this orbital. Okay, that again defines the shape of this orbital, which is now oriented along the y direction with the xy plane separating the two lobes of the orbitals, which must have different algebraic sign. Good. we have understood now all the 2p orbitals. Now let's see what happens if we go from a 2p orbital to a 3p orbital. And I'm discussing here just one of the three that there can be. We can look, for instance, here at the pz orbital. So like for the 2pz orbital, our angular part of the wave function is not a simple number. It's actually, again, a function of theta. But now for the radial part of the wave function, we have, in addition to this coefficient here, as well as this exponential term here, and that term here, r equal to a0, this term here in the middle, which is in brackets, 6 minus r over a0. Now, because of this term, we have now a spherical node. Okay? So not only will we have an angular planar node, but now also a spherical node in addition. You can easily see at which distance that spherical node should be. Can you see that? So this term has to become 0, and then you just have to resolve for r. Can you do this in the top of your head? So r should be equal to 6a0, right? Yeah. So at 6a0, this term will be 0. Yeah? Because then this is 6 minus 6a0. Okay, so a0 over a0 cancels out, so we have 6 minus 6, which is 0. Yeah. I can do it most of 0. So now you see the result graphic here. So here again, this is the amplitude of the wave function. You see that we have this term here, again at r equal to 0, the amplitude is 0, then we go through a maximum, and then we go here through our spherical node at 6a0. We go here through a minimum, and then the amplitude approaches 0. Okay, you see also here again the radial probability function, which now has 2 maxima because of that spherical node. Yeah. So the first maximum is here, then we have here our node, and then we have this big second maximum. So the radius at which the electron is most likely found would be the radius associated with this maximum here, and it's by graphical inspection at approximately 12 times the Bohr radius. Okay, so now, again, because this angle theta appears here, we also have an angular node, and we could again calculate that this is a planar node, which is in the xy plane. So overall, the shape of our orbit is now defined by a spherical node and a planar node. So we have again this dumbbell shape, which is induced by the xy planar node. In addition to that, these two dumbbells are further divided into two parts with different algebraic signs. Okay, here the first part, and here the second part. And here again the first part, and here the second part, due to the presence of the spherical node, okay, which now defines the overall shape of our 3p orbit. Okay, now let us go from the p orbitals to the d orbitals. So when we have a d orbital, then L is equal to 2, and for that reason, M can vary between, well, -2 and +2. That gives you 5 possibilities. -2, -1, 0, +1, and +2. So overall, we have 5 3D orbitals. So The one with m equal to 0 is the 3dz square orbital. It's shown here. Its mathematical form. So you see here actually the overall angular part of the wave function. You see it's a function of the angle theta. So again, we would expect a non-spherical orbital. Here is the radial part of the wave function. You see again, we have here our exponential term, e to the power of minus r over 3a0 in this case. We have here again this simple coefficient. Well, this is actually the entire coefficient. So this is also just a simple number, 2 over a0 to the power of 3/3. But now we have this additional term, r squared over a0 squared. Now, because of this term, at r equal to 0, again, our amplitude is being 0. Okay. So we first have an increase in amplitude, but then because of this exponential term, we go through a maximum and decline. Okay, so that looks again like this. Okay, so this is the amplitude of our wave function. At r equal to 0, it's 0. That's because of that term. Then we increase in amplitude, go through a maximum, and then we decline because of the exponential term. Eventually, amplitude becomes 0. Okay. You can again also calculate a radial probability function. That's the square of the wave function times 4 pi r squared. That is represented by this green curve. So also for the radial probability function, we would have a value of 0 at r equal to 0. We would then increase, go through a maximum, then eventually decline. So this radius here would represent the radius on which the electron could be found with maximum probability. Okay, so now what about the shape? Now the shape is again defined by this part of the wave function. And in order to determine the shape, again, it's helpful to transform this part into Cartesian coordinates. Okay. So now in Cartesian coordinates, this term becomes this term here, quarter times the square root of 5 over pi times 2z squared minus x squared minus y squared over r squared. So now you see in this case, all three coordinates appear. That is the difference to the p orbitals, where always just one coordinate appeared. So now this term here, 2z squared minus x squared minus y squared, mathematically describes the cone. Okay. 2z squared is equal to x squared plus y squared. So now for that reason, the angular nodes now describe two cones which determine the shape of the orbital. Okay, and you see the two cones here in red. So this is the first cone, and here this is the second cone. And again, the nodes separate the parts of the wave function which have different algebraic sign. Okay, so therefore, these two lobes here have the same algebraic sign, but this toroidal ring here, which is characteristic for the 3dz square orbital, has a different algebraic sign. Okay. So the algebraic sign switches as you go from here to this ring here, and again from this ring to the other lobe. Okay. So this orbital is oriented into z direction, okay? Because we have, well, 2z squared minus x squared minus y squared, just because of the mathematical shape. So overall, we have here two conical nodes to consider. So I see we are running out of time. We still have 4 other d orbitals to cover, but we can easily do this in the next class. So I think I will just stop here.